In this video, we're going to talk about parametric representation of surfaces. You recall from we were doing lines and curves, we often want to parametrize the lines in terms of, say, a parameter t. So we want to do the same thing with surfaces. We want to represent them parametrically. And so usually when we make a parametric representation, we'll have something of this form. Like this. So we'll have a surface represented this way, where this is a function of u and v, this function u and v, and this function u and v, where u and v are parameters. Again, it's much like we're doing with curves. Much like what we're doing with curves, except there we had one parameter t. Here we have two parameters. We're going to call these u and v. And there are several types of parameterizations you could use. Remember, we were dealing with curves, we have like a trivial parameterization. So one way would be to have like a trivial parameterization. And that would mean you would set, say, x equal to u and y equal to v. And so an example, represent 2x minus 4y plus 3z is equal to 15. Represent this parametrically. And again, if you use the trivial parameterization, you could just set, say, x equal to u, y equal to v. Then you put this down here. And then you would solve for z. So z would be equal to 15 minus 2x plus 4y, and z 15 minus 2x plus 4y divided by 3. And now let's put u and v in here. (15 minus 2u plus 4v divided by 3. So then our parameterization, like I say, we usually want to write it in this form, will be RU equal, the first one is U, Y is V, and 15 minus 2U plus 4V divided by 3, like that. So that's parameterizing this plane using the trivial parameterization, just setting x equal to u, y equal to v, then z, just solve for it. and you could put the u and v in at this point if you wanted to, right up here, and then solve for z, and you get this. So then x is u, y is v, and z is this equation here. Now, if you have certain types of surfaces, there are some very convenient parameterizations. So suppose you have a sphere. Let's say, again, remember, a sphere is x squared plus y squared plus z squared is a squared, where a is the radius. Of the sphere. And when you parameterize this, you can keep spherical coordinates in mind. Remember, spherical coordinates, and let me sort of write them down, then we'll kind of modify them. So spherical coordinates would have something like this. You would have x equal rho sine phi cos theta, y equal rho sine phi sine theta, z equal rho cos phi. So that was spherical coordinate. Now, for the parametrization, which you do, and let me write it over here. Now, when you do a parametrization for this, what you'll do is replace the rho with a, which is your radius. And usually, maybe we'll call phi, we'll call that u. And we'll call theta v. And you can do that the other way around. You could call phi v if you wanted to, and you could call theta u, either one, as long as you're consistent. So this would be the parameterization, and then so in this case here, let's say, let me actually do an example then. Parametrize x squared, y squared, z squared equals, say, 49. Again, we'll use this form over here, where x is going to, of course, the radius here is going to be 7. 7 sine u cos v. And then here, 7 sine u sine v. Z is 7 cos u. Now, one thing, again, important to remember is then, so this is just going to be a constant out here. So we're kind of using the same form that we had for spherical coordinates, but we're going to replace the rho, which is the variable, with the radius here. And also, so again, we need to know the bounds on these. Of course, you can see from what we have here, the U is playing the role of phi. So it's going to go from 0 to pi. And then V is going to go from 0 to 2 pi because it's playing the role of theta. So this would be what you would normally do. This is the most convenient way to parametrize a sphere. So, and if you want to write it out in terms of like what we had before, that's going to mean R UV is going to be equal, this is X, this is Y, and this is going to be Z, like that. Another common parametrization is a parametrization of a cylinder. Say suppose you have, and let me actually do an example. It would probably be the easiest way to handle this. So when we have given, say, x squared plus y squared is, say, 9, find the parametrization. And so let's take a look at this. Now, again, think of cylindrical coordinates or polar coordinates. When we did that, would have like x equal r cos theta, y equal r sine theta, and then z was allowed to vary. What's similar for the parametrization, you'll have like x, like in this case here, our radius is 3, x is 3 cos theta, y is 3 sine theta, and z can vary. Well, excuse me, let's change this. Let's use a different letter just so we don't make things too confusing. Now, some people will sometimes just keep the theta, but we'll use u here. And then z will be equal to v. So this is a parameterization that you could use for this. Again, so this is going to be a cylinder that opens up along the z-axis. Kind of like this. And obviously the radius is 3. So it could be sort of something like this. And we would get something roughly like this. Now, if you wanted to limit the size, let's say if you wanted this cylinder only to go maybe from 0 to z equal 4, then you would limit the value of z here. And so you could make it, like, for example, what you would do. So again, that's the answer to this problem. But let's say you wanted to limit this. So once again, we're going to put this into our equation here, like this. And then now, of course, u is playing the role of theta. So it's going to vary from 0 to 2 pi. And v, let's say you wanted to limit the z value, and maybe you want to start at 0 and end at 4, then you would put the limit on z to go from 0 to 4, which in this case would mean limiting v. So if we did this, then we mainly would have a cylinder that would start down here and end at z equal 4. Something like that. And now if it was opening up along, say, the x-axis or the y-axis, you kind of would follow the same pattern.